To see a full lecture room today, almost full. And thank you for coming, and hello to Junaid, Ruba, Yunus, and Rahama at a distance. So, we have 2 more lectures this week to complete the course. And what we want to do is I want to finish what we saw last time. This is kind of what we've been working towards really for the whole lecture, for the whole course. So last time we looked at piecewise affine full branch maps, right? So let me just review if we have piecewise affine full branch maps. And we showed that so a result about this is that Lebesgue measure is invariant and ergodic. Right? So this is true even if you have an infinite number of branches, right? So the fact that Lebesgue measure is invariant is a fairly simple exercise. I think it should be in one of the exercise sheets, right? So it's in the case in which it's finite, it's quite easy. In which case in which it's infinite, it's a little bit trickier, but we have here this infinite, okay? Finite or infinite, whatever, piecewise affine maps. And so this was also to start introducing the fact that both invariance and ergodicity are important in terms of studying the statistical properties of a map, right? Because Lebesgue measures invariant and ergodic, we have a lot of consequences. We can apply Birkhoff's ergodic theorem. We use this to get some results about in particular cases of 10x mod 1, some corollaries, but this is really the important result. So these maps have 2 characteristics. One is full branch and one is piecewise affine. So both of these play a role in the proof, of course, a very important role in the proof. And what we're going to do in these last 2 lectures is we're going to relax this piecewise affine property, right? So we used the fact that it's piecewise affine in this theorem in several ways. First of all, for the invariance of Lebesgue measure. So when you prove invariance of Lebesgue measure, you use the fact that you have several components here, and you really use the fact that it's piecewise affine because the derivative is constant in each component, right? So if we relax, so we want to look at maps where the derivative is not constant. Piecewise C1. And now, apparently, the techniques that we use, both to show invariance and ergodicity, do not apply here, right? The invariance is because if you take an interval A, of course, it will also have these components, but they will depend very much on the slope. The size of these, in general, they will not add up exactly to the Lebesgue measure of A. So the question is, do we have another physical measure? Remember, the reason we were interested in Lebesgue is because Lebesgue is a physical measure, right? So if Lebesgue is invariant and ergodic, then Birkhoff's ergodic theorem gives us conclusion for Lebesgue almost every point. So we want here also some kind of conclusion for Lebesgue almost every point, right? And if you remember, one way to do this is to get a physical measure, and for this it is sufficient to get a measure that is absolutely continuous with respect to Lebesgue and invariant and ergodic, right? So we would like question, does there exist a physical measure or a measure mu which is invariant, ergodic, and absolutely continuous with respect to Lebesgue measure. So if we have this, then this implies physical measure. Okay, so the first step we're going to do is we're going to formulate the concept of distortion. This is a very fundamental concept. We're going to move from the affine case to the nonlinear, to the world of nonlinear dynamics. So actually, before I do that, let me first give a specific example of this. So I cannot remember, I'm sorry, because I'm teaching at this moment this course in 2 different places at the same time. So sometimes I cannot completely remember what I've done here and what we've not done. Have we looked at the Gauss map?
Gauss map, there is all function. I said Gauss, it's called Gauss map.
So we have looked at the Gauss measure.
Yes.
Okay, okay. So let me just let this as an example. Thank you. So exactly. So we have the Gauss map. And the Gauss map looks something like this. Exactly, it's got infinitely many branches, 1/2. Oh yes, I remember, because we did the graph and then we translated it down. So, right, so this is 1/3, this is 1/4, so they accumulate here. And the graph looks something like this. Okay, so in this particular example, we already know that there's an invariant measure. Did I give you the invariant measure explicitly? Did we do that?
No.
We didn't do that, okay. So we had looked at the Gauss map initially, but I will show that we can define a measure mu. Let's call it Gauss measure mu is equal to 1/log2. So if A is an interval, so let's take, it's sufficient, remember, with the measures to define a measure on an interval, and then it automatically extends uniquely to all the Borel measurable sets. So we define it as this 1 + 1/x dx. So this just happens to be, okay, I'm not going to discuss how this was Gauss. Gauss found that this measure is invariant for the Gauss map. This is actually, because of the logarithms here, this is actually written explicitly as 1/log2 times log of 1 + b over 1 - b. So this is a probability measure, and I will leave it as an exercise to show that it's invariant. Because you can just explicitly, if you take an interval here, AB, you can actually compute, because we know the map exactly, so you can compute these infinite pre-images, right? And you can just use this formula to calculate the measure of all these pre-images, and you can see that the sum of them adds up exactly to the measure of A. Okay, it's just a computation that I will put as an exercise.
The measure doesn't depend on A, the definition? The starting of the interval.
Doesn't,
It's log 1 plus b over 1 minus b. So where
sorry. 1 plus b. I don't know why I wrote that. Thank you, Luba. Yes, thank you. Sorry. Yes, thank you. Okay, so this is one of the very rare examples in which we have an explicit formula for the invariant measure, right? So just like, remember, there was at some point we did also the topological conjugacy between two maps that had an explicit formula. It's a very nice example because you can check it, but it's very unusual, okay? So we're interested in the general case in which we have a full branch piecewise C1 map. This is an example of such map. In this particular case, we have explicitly this invariant measure we can check. And this invariant measure is clearly absolutely continuous with respect to Lebesgue because it's given by this density, right? So if you take a set of zero Lebesgue measure, it must have a zero measure. So mu G is absolutely continuous, but we don't know whether it's ergodic or not, right? Just like in the piecewise affine case, we knew that Lebesgue measure was invariant, but we didn't know whether it was ergodic or not, right? So this is no longer piecewise affine, okay? And so this is going to be an example, but we're going to prove a general theorem. And so we need to introduce the following concept. So F full branch map has what we call bounded distortion if there exists a constant k such that for all n greater than or equal to 1 and for all elements omega n in the partition Pn, which is the partition of the nth iterate of the map, and for all points x, y in omega n, we have this property here, log of the derivative the ratio of the derivative at these 2 points is bounded by k times the distance between the images. So we'll spend a little bit of time thinking about this definition. And what I want to do in the beginning of the lectures tells you what the results are. So first of all, let's think a little bit about this. So first of all, remember that if you have 2 points x and y inside omega n, as you know, the image of omega n is the whole interval, right? So the maximum, of course, this is bounded. We're in the interval anyway, so this is bounded. If we're in the unit interval, this is bounded from 1. So in particular, this means that this is uniformly bounded, right? And what does this say? So this is saying that if you take an element of the partition, remember that when you're taking higher and higher iterates, these partitions Pn, these elements are getting smaller and smaller, right? And Fn is mapping each of these elements to the whole interval 0, 1, right? So the derivatives are going to infinity intuitively, right? Because you're taking very small intervals and you're mapping it to the whole interval 0, 1. So this ratio is not easy to remain bounded, right? Because you are looking at very small intervals in which get mapped, which get stretched very, very much. The derivative is very large, and you may have at different points very different values of the derivative. Right? So what this is saying is that this is uniformly bounded. You can think, initially you can think of just this. This is a stronger version of this, but initially you can think of the fact that it's just uniformly bounded. As you take larger and larger iterates, you look at elements of the partition, and the ratio of the derivative fn at two different points is uniformly bounded. In particular, if f is piecewise affine, what is the value of this if f is piecewise affine? The left-hand side is 0. You see that? Ling, you see that? Yeah, Toluwane? No? What does piecewise affine mean?
Then it is, the ratio is 1.
Exactly. So piecewise affine means that on each branch, the derivative is constant, right? And if your map is piecewise affine, all the iterates of the map are also piecewise affine, okay? So if you take any 2 points inside one element of omega n, and you take the derivative at any 2 points, it will be the same. That's what piecewise affine means, right? So this is a good way to develop some intuition for this, right? So the distortion is 0 in the piecewise affine case. So this is a straightforward generalization. It's saying instead of being 0, we want it to be uniformly bounded by a constant k that is independent of n. Another way to think about it is that if you take something that is nonlinear like this, where the derivative is different, and you take two nearby points, right, and you iterate it n times, then the left-hand point will pick up the derivative along its orbit. By the chain rule, you just multiply all the points along the orbit. The right-hand point will also pick up along the orbit. These two derivatives will be different, right? And it is conceivable, in principle, that maybe the right-hand point is always larger. If you have 2 points and the derivative at the right is always bigger than the derivative on the left, then as you keep going, the ratio between them is increasing, right? Because the derivative along the right is increasing faster than the derivative along the left. And so this ratio is blowing up, right? This property is saying that this does not happen. So we will work with this property. It's not a trivial property, okay? And we will see also how to check it. It's also, when you look at it like this, not easy to check because it requires, it's a condition on all the iterates, right? But I would like that at the end of these two classes, and when you've looked at the notes and the exercise, you are very familiar with this concept of bounded distortion. It is a fundamental concept in all kinds of differentiable dynamical systems because it's really a way of controlling what happens in many, many different situations. It is a very important quantity to evaluate. So what's the motivation behind this? So the first theorem, so we'll first summarize the results that we're going to prove to motivate it, and then we will start doing the proofs. So if that F has bounded distortion, if F is a full branch map with bounded distortion, this implies that Lebesgue measure is ergodic. So we shall see that this, in some sense, the bounded distortion is really what is really that a slight, but at the same time very big extension of piecewise affine, and it is sufficient. In fact, the proof of ergodicity will be almost the same as what we did for the piecewise affine case. If you remember, we discussed last time there was just one point where the piecewise affine was used, and when we look at the proof, we will see that we can replace it. If we have this, then we can get an inequality instead of an equality, so we will have a look at that. But of course, ergodicity is not much good. We need to do two things. So in this case, we would need to check if we want to get, sorry, let me go step by step. So first of all, in the general case, we also want to find an invariant measure. So we will prove, let me write it also here. Can you see down here? Yes. So theorem is that again, if F has bounded distortion, then it implies that there exists a unique invariant probability measure mu, which is absolutely continuous with respect to Lebesgue. So the problem is that these are two different measures, right? Lebesgue is ergodic and mu is invariant. What we would like is mu to be ergodic, and we have it with this simple lemma that says that if, in general, if F is a measurable map and mu1, mu2 are probability measures with mu1 absolutely continuous with respect to mu2, then if mu2 is ergodic, it implies that mu1 is ergodic. So this I will leave as an exercise because this is really just checking the definition of ergodicity. Okay, but if we apply it in this case, then that is very good, right? Because what we've shown then is that Lebesgue measure is always ergodic, and therefore any absolutely continuous measure with respect to Lebesgue is also ergodic. And in particular, since we've shown that there exists a unique invariant absolutely continuous measure, then this measure is also ergodic, right? So as a corollary, combining these three results, we show that if F has bounded distortion, then this implies that there exists unique invariant ergodic measure mu, which is absolutely continuous with respect to Lebesgue. And therefore, it's a physical measure. Any questions? So what remains, of course, this is all very good with this condition, except that this condition may or may not be ever satisfied, right? It might be that the only times it's satisfied is the piecewise affine case. So we need to write down some conditions that allow us to check it. For example, so far the results are put on the board still do not imply that this Gauss measure is ergodic, right? Because we haven't checked the bounded distortion. So we know that we have this invariant measure that is absolutely continuous. If we can show that this satisfies the bounded distortion property, then by this first theorem, we have that Lebesgue measure is ergodic, and this implies that this measure here, which is invariant and absolutely continuous, is also ergodic by the lemma, and therefore we would have that this measure is ergodic. So the final proposition is that if F is a piecewise C1, uniformly expanding full branch map, full branch, such that it satisfies also the following condition: supremum over all intervals omega in P in the partition, and the supremum over all xy in omega of f prime of x, sorry, f double prime of x over f prime of y squared is finite. Okay, then F has bounded distortion. Excuse me?
Measure is small.
So very often it is defined like that, because in practice, we always use the concept of ergodicity for invariant measures, right? But I think it's, so the definition of ergodicity does not need invariance. So the definition of ergodicity is just that every fully invariant set has measures 0 or 1. No. I think it's useful. In fact, it's only the last few years that I've started realizing how useful it is to emphasize the independence of these two definitions, for example, in this setting, right? And it's only really the relevance of using the definition of ergodicity independently from the definition of invariance is useful only in this kind of situations, you know, because this is a slightly stronger, well, it allows us to separate these two results, right? Because in this result, we do not need to know anything about the existence of any invariant measures or anything. Just Lebesgue measures ergodic without knowing anything about the existence of any invariant measures. That's right. Yeah, that is usually how it is formulated. But I think it's more useful to separate the two definitions. In fact, there's more and more, even recently, there's some research, you know, there really are some results sometimes that you can get for ergodic measures even without the invariance somehow. It's useful to separate the two, okay? So you see that formally they're independent, the definition, right? Because you say you take a probability measure, and you say any fully invariant set, f minus a equals a, has measure 0 or 1. There's no reason for the measure to be invariant. Any other questions? So I hope that we will be able to give most of the proofs. So I will give you the notes that have the full proofs of all these results. Some of them are a little bit technical, require some computations, but really none of them are particularly difficult. I will, in the lectures, I will try to give the main ideas and focus maybe on the main points of these, and then you should look at the notes to make sure you can follow all the details. Let me say that this as I said here, we are really, there's two properties of the maps that we are trying to generalize. So the piecewise affine we can relax to the bounded distortion. And this is a very, it turns out to be a very broad generalization. So as you can see, we have the conditions for bounded distortion here, which are not so restrictive. We want it to be uniformly expanding. We want it to satisfy this condition, which is a bit technical, but you can check for the Gauss map. So I forgot to say that this is, I will leave it as an exercise again to check that the Gauss map satisfies this condition. So corollary is that the Gauss map has bounded distortion. So of course, the main difference between this, the fundamental difference between these conditions that imply bounded distortion is that these conditions can in principle be checked just from the one iterate of the map, right? Or at least from a finite iterate. So the fact that C1 is uniformly expanding, for example, if the derivative is bigger than 1 everywhere, or in the Gauss map, you can show that the derivative of the second iterate of the Gauss of the map has derivative bigger than 1. So that gives you the uniform expansivity. And this is a condition that just depends on the map. So you look at the Gauss map, you look at the formula for the first derivative, you look at the second derivative, you look at what the maximum and minimum is between the first and second derivative in each of these branches, and you see that that ratio is uniformly bounded. Okay, you just check. You just explicitly calculate the first and second derivative, you calculate these positions here, and you show that this ratio is uniformly bounded. Okay, so this depends just on the first iterate, so you can actually check it. So it turns out that many full branch maps have the bounded distortion property. Okay, now the next step, again, just to give some general concept before we get into technicalities, is how special is the full branch? Because of course here we are building up a theory of dynamical systems, right? We're trying to develop techniques that will work in a lot of cases. So even if you look at the one-dimensional maps, it is clear that full branch is still quite a strong condition. Right? So if you just take a one-dimensional map on the interval, it's not going to be full branch. It's just a one-dimensional map of the interval to itself. So let me say that there is a very big theory in which it turns out that full branch maps play a very important role. And it turns out that for many maps that are not full branch, they kind of contain a full branch map hidden inside this. Okay, I won't have time, unfortunately, to give the formal definition, But for many maps that are not full branch, you can find a set, an interval A, and when you look at the return map to A, you get a full branch. This is called an induced map to some set A. You get a full branch satisfying bounded distortion. And this is one of the key techniques that has been used in the last 20 or 30 years to prove the same kind of results. So the kind of results we're always trying to prove is the existence of a physical measure, right? In one dimension and also in higher dimensions, the easiest way to construct a physical measure is to get an invariant ergodic absolutely continuous map. And the easiest way to get this is to have a full branch map with bounded distortion. Okay, so you can generalize this concept of full branch bounded distortion to higher dimensions as well. And basically you get the same theorem. Okay, but if you have a map that is not full branch, it turns out that in many cases you can construct an induced map that is full branch. And in fact, there are also some results that show that basically any map that has an invariant ergodic absolutely continuous measure has an induced map that is full branch. So the reason why I'm giving you all this discussion is to kind of justify a little bit that even though full branch maps look very special, you know, as often in mathematics, you shouldn't feel bad that it looks like you're doing something special because you build up and in the end you realize that it's not as special as all that, that actually you can use these techniques also in much more general cases. So, so this is really the foundations for much more general theories that kind of build on these results. These results here, historically, I would say that they go back to the 1950s. So they're quite classical results, this kind of here, this bounded distortion and these results for full branch maps. And since the 50s, there has been lots of generalizations to many other maps. And many of these approaches involve, as I said, this kind of inducing method. For example, this could be an interesting project for some of you who might be interested, is to look at these induced maps and how you construct full branch maps inside more general maps. That would be the next step. If we had more time, this would be the next chapter in my lecture notes, would be this. Okay, so where shall we start here? So, let's start with this theorem here. Call this theorem 1, theorem 2. Okay. So ergodicity. How do we show that Lebesgue measure is ergodic? We really want to repeat very closely the argument for the piecewise affine maps. So we need to understand, first of all, a little bit better what this condition really means, right? And so I'm going to start with a geometrical interpretation of what this means. So let's suppose we have an interval J here. And we have Fn. And we have here Fn of J. And then let me write D is equal to the distortion of Fn on J, which is just equal to the supremum for all x, y, and j of df n of x over df n of y. I take 2 points here, x, y, right? And I take the derivative. This is fn of x. This is fn of y. So the lemma says that for any subinterval so let's take subinterval j, then we look at the image fn of j prime, j prime, fn of j prime. So if we look at the ratio between the size of fn of j prime and fn of j, and this is bounded above and below by e to the distortion over the ratio between j prime and j, and e to the minus d over the ratio between j prime. So how does this apply to piecewise affine maps? If this Fn was affine, what would it imply in particular? Right? So in the affine case, we have that this is equal to 1, right? Because if this interval, if this map is affine, it means the derivative is constant. That's what we mean by affine, right? So it means that this ratio is 1. Sorry, this should be log here. Exactly. Exactly, which is, of course, obviously the case in the affine case, right? We don't need this lemma in the affine case. The affine case, we know, because the derivative is constant, this is just a uniform stretching or contraction or whatever. At every place is the same. So in the affine case, it's clear that these ratios are preserved. We use that. Remember that we use that in the proof of ergodicity of Lebesgue measure for piecewise affine maps. We used at some point the fact that the ratio between a subset and the set it contains is preserved in the images, right? So if you take an interval that is half the size of this, right? If it's affine, the image will be half the size of the image, right? The ratio is exactly preserved. And the geometric interpretation of the distortion, in fact, this is really why, this is the property we want, right? This lemma is the explanation of exactly, in some sense, geometrically how bounded distortion keeps you close to the piecewise affine case, right? It's telling you that, because in principle, if the derivative is different, right? For example, here, that you're mapping this interval to the whole of 0, 1, right? The derivative is different here than here, right? So if you take a small interval here, that is a certain proportion of this interval, then its image will be a certain proportion of this. But if you take the interval of the same size here, the derivative is different, so the relative proportion changes if the derivative is not constant, right? And so if you look at this, the fact that this bounded distortion is uniform, this constant here, K, yeah, K is really D here. Maybe I should have used the same constant here. It's uniform for all n, for all omega n when you take Fn, right? So what this is saying is it doesn't matter how deep you go in the partitions, right? You take a very large n, so you have very small elements. They will map onto the whole interval 0, 1, and they will always map in such a way that proportions are preserved up to uniform constants. D does not depend on n, right? That is really, this D is really the same case. Sorry, I should have used probably the same notation here. So this is the image that you should have of what bounded distortion really means, right, geometrically. This is the crucial picture of what bounded distortion is. So let me sketch some of the steps. This is very easy, actually, the proof of this. So as you expect in one of these situations, you're really comparing intervals with their images. So you use the mean value theorem, right? So by the mean value theorem, there exists x in J prime such that dfn of x is equal to the ratio fn J prime over J, right? So there exists an average derivative. If you compare this to its image, right, by the mean value theorem, there is some point here that has exactly that ratio. That's the average expansion. And similarly, there exists some y in J such that the Fn of y is equal to Fn of J over, sorry, this is J prime, sorry, over J, right? And therefore, we have that so we have that this ratio dfn of x over dfn of y is equal to fn of J double prime over J double prime over that, so we can write this as J over Fn of J, right? And this is just equal to okay, it's just this. So this is now yeah. So we know that this here, by definition of distortion, this here is this D is the supremum of these ratios over all x and y, log of this. Sorry, so maybe, yes, so yes, I'm taking exponential. So this is greater than or equal to e to the minus d, and this is less than equal e to the d, right? These two are equal. I know by assumption, by the definition of d, that this holds for this, so it holds for this particularly, and therefore we just get the result, okay? So you just, now, you get fnj double prime, fnj, sorry, I'm getting a bit confused here. So fnj prime, fnj, okay? So this gives the result. Okay, you take fnj prime over fnj less than equal to ed, and you take this j over j prime, you multiply here, you pull it out here, and you get that. Okay, and then remarkable fact is also the following, is that if f has bounded distortion, then the supremum over all omega n in Pn of the size of omega n tends to 0 as n tends to infinity. So we proved something similar in which setting? Do you remember? We proved exactly the same thing. Exactly, in the uniformly expanding case. Exactly. Exactly, absolutely. That is a very good remark. So in fact, it does not formally imply uniformly expanding. The other way is almost true, right? If we have uniformly expanding and this, then it implies bounded distortion, right? Yes, I do not think, so that is actually a good question. That is actually an interesting question. It might be an interesting little exercise to check, to try to find a counterexample. I think that, so the conclusion is true. So bounded distortion implies this conclusion, okay? But I do not think that, in fact, this came up with a discussion recently with a colleague, whether bounded distortion implies uniformly expansion. Maybe you can try to see, I conjecture that it does not, but I do not have a counterexample in mind, right? And it may be that, so in the finite case, okay, that's a good question. I've thought about it recently, actually, but I did not sit down to really try to work it out. I'm not sure what the answer is. Certainly, to prove this, it does not use any uniform expansivity, and that's why it is an interesting proof, actually. So I will sketch a little bit the argument here. So again, usually in the literature, this property of bounded distortion is not so much highlighted the way I have done it in this course. Usually you always assume uniform, you always assume those conditions here. Most of the time, you will see these results basically assuming this condition here, and then proving these results that I've mentioned. But actually, some of these results do not need those conditions. They just need the bounded distortion. So I've tried to emphasize that here. So how do we prove this? This is quite interesting. Okay, so write it like this. Let delta is equal to the maximum overall omega 1 in P1. So P1 is the element, is the partition of the original full branch map of the size of omega 1. So this is the biggest interval of this partition, right? So we have some kind of full branch map. And clearly we have the biggest interval here. This size here is delta, even if it's infinite. And then, so what do we have? This situation here is that we have for all n greater than or equal to 1, we have that, as we know, Fn maps omega n I, and Fn minus 1 maps omega n to some omega 1 in P1, right? Remember, this is the way the properties of these subintervals is that they always map to the partition element of the higher level, right? So if you take an element of omega n, it will map after n plus 1 to some element in P1, and then you apply f one more time, and it maps to I, right? So then this maps to I after one more iteration. So this means that Fn minus 1 of omega n, the length of this, is less than or equal to delta, right? Because this maps to some element of P1, and all these elements have size less than or equal to delta. And this means that so if you remember the way these partitions work is that we have here, we have this element omega n, and this element here, omega n, belongs to some omega n minus 1, right? And then when you apply Fn minus 1, this is the whole interval 0, 1, right? And omega n minus 1 maps to all of 0, 1, and omega n maps to some omega 1, right? So omega 1 is equal to f n minus 1 of omega n, and 0, 1 I is equal to f n minus 1 of omega n minus 1. Okay? Stop me if I know it's getting a little bit technical, but I think these last two lectures we have no choice at this point. So if you remember the way the full branch maps work, right? You have this nested sequence, all these omega n's are nested. So omega n belongs to some omega n minus 1. Omega n minus 1 belongs to Pn minus 1, and it has the property that after time Fn minus 1, it maps to the whole interval, right? And every omega n belongs to some omega n minus 1, and it maps to some omega 1 in P1. So what does this mean? It's not clear where we're going here. I completely appreciate that because this is a little bit mysterious. But what this means is that if we look now at the complement of this, there's a little kind of magical step here. So this means that if we take the measure of Fn minus 1 of the complement n minus 1 minus omega n, this is made up of these two components, right? So here we have omega n. This is the image omega n. So this is greater than or equal to 1 minus delta, right? Because if n minus 1 of omega n, which is this, is less than or equal to delta. So the image of the complement is greater than or equal to 1 minus delta. And therefore, we have that, let's see. And therefore, we have here that okay, so we're going to use this lemma here. We're looking at the image. This has two components, but you can just take the union of these components. So this is saying that omega n minus 1 over omega n over omega n minus 1, right? So the ratio between the complement of this and the interval itself, how does that compare to the ratio between these complements and the interval itself? By using that lemma, this is greater than or equal to e to the minus d times the image f n minus 1 of omega n minus 1 minus omega n over Fn minus 1 omega n minus 1, right? So I've just taken Fn minus 1 on both sides, right? And now I've just used, instead of using the fact that it's affine, I use the bounded distortion to get this inequality. And this here, by what we just said, this is greater than or equal to e to the minus d. And this is 1 minus delta. And what is this? This is 1, because this is just the whole interval, right? So this is e to the minus d, 1 minus delta. You mean in the case it's not a unit interval? This? Yes, thank you. So is this number bigger or less than 1? E to the minus d times 1 minus delta. e to the minus
Less
d is
than
it?
1.
Sorry?
Less than 1.
Yes, because e to the minus d less than 1 and 1 minus delta is less than 1. Okay, so I'm going to write this as equal to 1 minus tau. Okay, I'm going to define tau in this way. It's easier just for the next step. So we're almost finished, but just I'm going to write it as 1 minus tau because it's easier. And then I'm going to write this as okay, so what I'm trying to do, what am I trying to do in this whole case? Let's just remember what we're trying to prove, that this goes to 0, right? And so the easiest way to show that this goes to 0 is to show that every step you reduce by a factor, right? So that each omega n is less than equal tau times omega n minus 1, right? So that you're shrinking exponentially, just like you do in the uniformly expanding case, right? Even though this is not necessarily uniformly expanding. So, exactly. So this is omega n minus 1. That's a good observation. In motion, this is over omega n minus 1, right? And this here, we can just write as 1 minus omega n over omega n minus 1. And so this means that this is greater than or equal to 1 minus tau. Okay, so 1 minus this is greater than or equal to 1 minus tau. So this implies that omega n over omega n minus 1 is less than or equal to tau, which is strictly less than 1. Yes, exactly. Okay, so this completes the proof because it shows that every time you shrink by a definite factor tau. So you start, this is just a general statement, so it shows that you start with a certain partition, and then you look at the partition P2, and every element inside that partition is at least a factor of tau smaller than the partition in which it's contained, so they're all shrinking exponentially fast. So maybe this can be used to show that a bounded distortion implies uniform expansivity, actually. I would actually be curious to see. I'm not sure if it's possible or not, but okay. So how then do we finish proving ergodicity? So I will not do the whole proof because we have all the ingredients of the proof. So this, remember, how did we use this for the proof of the ergodicity of Lebesgue measure? So let me, wait. Okay. Exactly. The Lebesgue density theorem. So, okay, so I will not give the full proof again, okay, because you looked at it already, but in the proof, so proof of ergodicity. Lebesgue. So basically, at some point, I think the notation I have here is a little bit different from what we had before, but at some point, we were looking, sorry, the notation I have here is a little bit different from the one I had in the proof, because here we had, in the end, we had f of a, right? So we had f of a equals a. We had Lebesgue, a is positive, okay? And then we had some n, some omega n, such that the intersection with the complement of a over omega n was less than or equal to epsilon, is that right? And then, let's see, I'm trying to translate because I have it a little bit different here. And then we have that, so this is our omega n, this is our Fn, so this maps into I, this is Fn of omega n, right? And then here we have the set A complement. Then here we have the set Fn of a complement, section omega n. And then we had, so what we get from this is what we wanted to show. Is that, yes, so this we showed that this is actually equal to a complement, right? So we had that a complement, sorry, yes, so a complement is equal to Fn of AC intersection omega n over Fn of omega n. And now we use the bounded distortion to say that, so here in the affine case, we got an equality and we showed that this was equal to this, right? Whereas here we get that this is less than e to the d times that, omega n intersection a complement over omega n, right? I've been able to reconstruct this is less than epsilon, yes. Oh, I see this one here. You're right. You're right. Thank you, Mokshin. You're right. So technically, I cheated a little bit, yes, because I stated this lemma for intervals, and I'm applying it to measurable sets. So you're right. So we need to justify the fact that this extends to measurable sets also. Yes. So you need some measure theoretic argument to show that this extends to measurable sets. It does. Yes. 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 That's an important technical point. Okay, you're right. So really, we need this interval to hold for measurable sets because that's how we're applying it. Anyway, the key point really is that here, this is where, if you remember, this was the proof we use Lebesgue density theorem to show this, right? That for n sufficiently big, we could get some small interval omega n where arbitrarily much of the measure belong to A, so arbitrarily small of the measure belongs to the complement of A, and then we use the piecewise affine to get equality here, okay? But as we remarked at that time, all we need is an inequality because all we need is this less than equal to epsilon, and this is exactly where the distortion holds. Okay, so to summarize, the ergodicity of Lebesgue measure for full branch map satisfying bounded distortion uses these two lemmas. This one here, which is just the geometric interpretation. The geometric interpretation of the distortion, okay? And as Milmukshin correctly said, I should have said that this extends to arbitrary measurable sets. And then the fact that the bounded distortion also implies this important consequence, this important ingredient that we use in the proof. And then we put these two together and we get essentially exactly the same proof to prove ergodicity of Lebesgue measure. And this is interesting that we can do this without any discussion about invariant measures, right? So you see that this is nice because it's really a proof that does not assume or use the existence of any absolutely continuous invariant measure or anything. It's really about Lebesgue, right? And this will automatically imply that any absolutely continuous invariant measure is also ergodic, right? So this is a kind of a stronger statement in some sense. I think maybe we might stop here today, actually, because there's two other things left. We want to show now that there exists an invariant measure, absolutely continuous, right? That's a very interesting argument. It requires some approaching it from a slightly different point of view. And then the calculations which allow us to check the bounded distortion property, right? Those two results are what's left. And I don't think I can do either one of them in the next 10 minutes. So I think it's better just to finish here, give you a little bit of time to absorb what we've done today, if possible. You know, familiarize yourself with this idea of bounded distortion, with these lemmas here, so that you're then more ready to follow the arguments on Thursday. Okay, so let's do that. Any other questions before we finish? Yes? Okay, I think we can finish a little bit early today. Thank you.
Thank you.
Okay.